In this video, I will write a recursive function for inserting in a binary search tree as well as a recursive function for deleting from a binary search tree. Already we have written a program for creating a binary search tree, and the insert function was a repeating function, that is iterative function. Already we have seen it. In the same program, I will add a function for recursive insert. Let us write a function. It returns structure node pointer, and the function name I will call it as rinsert because already I have used a name insert for iterative insert function. So it should take a pointer to a root node. So let us call this as a P, and that is a root node, and the key that we want to insert. Now this recursive insert works just like a recursive search function which we have already discussed on whiteboard. So the same method I will follow. Let us start writing the code. If any variables are required, I will declare them afterwards. First thing, if the key is less than P's data, that is root's data. If it is less than root's data, then we should try to insert on the left hand side. So call rinsert upon left hand side of P, that is L child. And the key is the parameter. These are the two parameters. Now this function is going to return the address of a node that I will take it in left child of P. Then else, if key is greater than P's data, that is root's data or the key's data, then I should call upon recursive function should be called upon right child, and its address should be taken in R child. Else means the key is equal, so it's already present there. So we don't have to do anything, simply return P. And even after insertion, I have to return P only. So I'll just write P in every case. So it means else if they are equal, I don't have to do anything. Then when to insert this one? See, while searching, when we reach at a null, when P becomes null, that time we should insert a new node. So in the beginning, I will write on the code now. If a P has become null, means we have reached the last, that is leaf node. Then create a new node. So I'll take a temporary pointer T, and with that I will create a new node, struct node pointer, and I should call malloc function for creating a new node. Size of struct node. So node is created. Inside this node data, I should set the value, that is key, and also I should set its left child as well as right child as null, T's left child and T's R child as null, and return T, so that T is set to the parent node as a left child or right child. It depends on how we were searching. That's it. So for this I need a pointer, that is struct node pointer T. This T I can keep it initialized to null. That's all. This is a recursive procedure for inserting in a binary search tree. Now let us go to the main function and let us use that rinsert function. See, when I call rinsert function for the first time, when I am creating first node, then I should assign this to root. So this should be root assign rinsert. First time I am inserting 10. Then rinsert, and also I should pass this root as parameter in every call. Then rinsert, I should pass root as a parameter root, because it's recursive. It should take the parameter, the pointer of root itself, and all these functions are rinsert. I will modify them. See, only the first one I have to take it in root, because when I'm creating first node, when it returns the pointer, that should be taken in root. That's all. Remaining, already I have a function for checking in order traversal, so it will print in order traversal, and also checking a key element whether 2 is present or not. So this time we will check for 20 whether it's present or not. Let us run this program. Yes, it's working perfectly. A binary search tree is created. 5, 8, 10, 20, 30 is the in-order traversal, and 20 key is also found. Let us debug this and see how this tree is created. First is root is 10, then its left child will be 5, then right child of 10 will be 20, and then 8 will be on the right hand side of 5, and 30 will be on the right hand side of 5. So actually the structure that we should get is, so here I will draw and show you, just rough sketch I am doing it here. 10 should be in the root, and 5 should be on its left hand side. This should be 5. 20 on the right hand side of 10. This should be 20. A tree should be created like this. And 8 should be on the right hand side of 5. This is 8. And 30 should be on the right hand side of 20. So the keys should be inserted like this. This should be 30. Let us debug our program and check whether the tree is constructed like this or not. I'll put a breakpoint on in-order traversal. Before performing in-order traversal, all the nodes will be inserted. So let us see how the structure looks like. Let us look at the debug area. Root is there. Root is having value 10. Yes, perfect. Its left child is 5. Yes. And 5's left child is null here. It is null here. And 5's right child is 8. Yes, it is 8. And its left child and right child are 0. Yes, that are nulls. Then let us close this. Then 10's right child is 20. Yes. And its left child is null. Here we can see that it is null. And 10's right child is 30. Yes, perfect. So that's it. It is perfectly inserting and creating a binary search tree. I'll stop this one. Now let us write a delete function. Delete function will be a recursive function just like a recursive search or the recursive insert we saw. So let us start writing it. Struct node. It will return a pointer to a node. Delete function. So it should take a parameter as struct node pointer. Let us call it as p. This is going to be a root and integer key that we want to delete. Then inside this function, I will write on the similar code that first if key is less than p's data, then we will perform search upon left hand side. So p's l child is assigned with delete function which will call itself again on p's l child. Then else if key is greater than p's data, then it is on the right hand side. So we should search an key element on the right hand side. So that will continue on the right hand side by assigning it to r child of p called delete function by passing p's r child as well as key also it's taking, and here in the previous one also I should write key. Yes, now it's okay. Now else means both are equal, means key is found, and this time we have to delete a key. So for deleting a key, already I have shown you how a element is deleted from binary search tree. We can delete an element by replacing it with pre-order. We can delete an element and replace it with the in-order predecessor or in-order successor. So we have two options here. So here I would like to decide which one I should take. I will not blindly follow predecessor or blindly follow successor, but I will decide based on the height of left subtree and the height of right subtree. If the height of left subtree is more, then we will delete an element from the left hand side. Otherwise, we will delete an element from right hand side. If they are equal, we can delete from any side. So let us check the height, and based on the height, we will decide whether to delete from left hand side or right hand side. So first of all, I will find height of p's left child. If this is greater than height of p's r child. Yeah, I have to write on this function height. I'll write it afterwards. So if p's left child is greater, so if p's left child height is greater than right hand side, then we should delete an element from left hand side. So for deleting an element from left hand side, actually we need a in order predecessor. So for that I will write a function which will find out in order predecessor. So that function I will write down directly here. I will call that function in pre of left subtree. So that is P's L child. So how to find the in order predecessor? It should be a rightmost child of left subtree. Yes, we will get that one. And this I will take in a temporary pointer, let us say Q. Then after finding that element, I should copy the data of a Q. I should copy the data of that in order predecessor in the P's data. So P's data should be changed to Q's data. It should be replaced. Then after replacing, I should delete that node Q. So P's L child should be assigned with, again called delete recursively upon P's L child by a new key. We have to delete this key, that is Q's data we have to delete. Yes, this will recursively call itself. Means we have already seen that while deleting, we may have to modify more than one keys or more than one nodes. So how this work I will show you. For this I will draw a diagram and show you. So here is an example binary search tree. Suppose I want to delete 50, then it is not having any right child, so I should get an element from left subtree, that is in order predecessor. So in order predecessor for 50 is 40. So this value should be copied here. Then this node should be deleted. But again, this node is having its left subtree, so its in order predecessor is 30. So 30 should be copied here, and we should delete the node 30. So this is how it is calling recursively itself. Then finally we delete node 30 because it's a leaf node. So physically this node will be deleted, and value 30 is copied here and value 40 is copied here. In this way 50 is deleted. So the physical node deleted is this one, the last one, the leaf one. So that's how we are calling it recursively. So back on this one, if the height of left child was more, then we have perform on the left hand side. Otherwise we will perform the same thing on the right hand side. So I will take it in else and I will paste it directly the same code. So this time I have to find in order successor upon right child, and this right child, and this also should be a right child. That's it. So recursively perform deletion on the left side or the right hand side depending on the height. Now finally, when I should delete a node, so here I should delete a node, here I should delete a node. If P has became null, means it has become null, actually nothing we have to delete, so simply return null. And second thing, if P is a leaf node, so P is a leaf node means P's left child is not there, is equal to null, as well as P's right child is equal to null. If both are null, means it's a leaf node, and when it is a leaf node, directly we have to delete this node. So here I will write on the code for freeing that node. Free P. P should be freed. And before freeing P, let us check if P is a root node. If P is equal to root node, P is equal to root, then root should be made as null. So we should delete that node. Yes. Then after that we should return null because the node is deleted. That's all. This is the code for deleting. See, this portion is like search process only, and when the key is found, so we have to replace the element by finding in order predecessor or successor. So I have taken an option depending on the height, and when we have reached the leaf node, we should delete that node. And we should also make sure that if this was the last node, that P is equal to root only, then root should be made as null. Then here the required variable I will declare, that is struct node. I have taken a pointer that is Q, so I will declare it. Then above this, I should have functions for finding height and in order predecessor, in order successor. So the function for finding height, it should take struct node pointer P, and if P is equals to null, then return 0. Otherwise, I should find out x value and y value. X is height, P is L child, Y is height, P is R child. Then return whichever is greater. So already we have seen this code, so I don't have to explain, just I am typing it. Return x plus 1 or else return y plus 1. This is for the code. This is for the height. Then in order predecessor, it should return a node structure, that is in order predecessor, and it should take the parameter also as node structure. Let us take it as P. Now from the point that is node P, we should find out in order predecessor. So it's a rightmost child. So while P as well as means P should not be null, while P's R child is not equal to null, means it will be going on moving on the right hand side. So rightmost child we will take of left subtree. And finally, it should return P. Now the same way, I will copy this and I will write down the code for in order successor. So I will just modify this. I'll just give some line gaps so that you can clearly see the code that I am typing. This is for in order successor. In order successor. So it should be going on the left hand side now, that is leftmost child of right subtree. That's all. I finished all the function. I have just typed all of them without checking any errors. Now if I compile, if there are any errors, I'll remove them. There's an error. Yes. End of the function. Yes. Inside this recursive delete, at the end, I should return P. Return P as same as what I was doing in insert function. Let us run this. It should run error free. Then we will use delete function. Yes, it's working perfectly. Now let us call delete function. So from these nodes, I will delete one element. So before performing in order traversal, let us call delete function. I will call function name as delete, and we should pass root, and the key that I want to delete is 20. So 20 should be deleted from binary search tree. Let us run this. Yes, 5, 8, 10 and 30. It's working. Let us delete root itself, 10. 5, 8, 20, 30. Let us create this extreme case, that is 50, 10, 40, 20 and 30. If I insert them in this order, I'll get this structure. Then we will delete 50. So root is 50, then its left child is 10, then right child is 40, then left child is 20 and the right child is 30. And we will delete 50. Let us check whether it will delete 50 or not. Yes, deleted. If I delete any other element like 30, I want to delete. Yes, 30 is deleted. You can check your results here, right? So 30 is deleted. So it's working perfect. So that's all. These programs are a little lengthy and you have to work carefully. And whenever you require, you can do some paperwork also to check how your results are working. And debugging the program is more important if you're getting any errors. And always you have the solution available as PDF below the program. So you can download that PDF and you can compare your program with the PDF. That's all in this video.